Good morning. My name is Elizabeth Fossamala. For my Nuclear Energy Engineering Technologies degree at Thomas Edison State College, I'm writing a research paper with a group of other students about the benefits of using thorium rather than uranium as fuel in a nuclear reactor. Although our paper looks at a wide variety of aspects concerning this, I'll be focusing my attention today on some of the topics I personally researched and found interesting. Specifically, the basic difference between uranium and thorium, the energy potential of each, why some countries are starting to seriously consider thorium as an energy option, the basic reactor types, and the steps required to license a thorium reactor in the United States. This video is designed to be viewed in concert with a PowerPoint presentation I put together. If you follow through on the slides as you watch this video, it'll give you some awesome visual aids. The difference between uranium and thorium. There are actually a lot of differences between uranium-235 and thorium-232. I'm only going to focus on one difference today, and that is the fact that uranium-235 is fissile, which is a necessary part of producing heat in a nuclear reactor, and thorium-232 is not. There are in fact three fissile isotopes that can be used in a reactor: uranium-233, uranium-235, and plutonium-239. Of those three isotopes, only one can be found with any reasonable abundance in nature, and that's uranium-235. The other two isotopes, although non-existent in nature, can be produced in a neutron field from very abundant isotopes of uranium and thorium, respectively. The very abundant uranium-238 in a neutron field can absorb a neutron, beta decay twice, and become the fissile plutonium-239. The very abundant thorium-232 in a neutron field can also absorb a neutron, also beta decay twice, and then become the fissile uranium-233. When we discuss thorium reactors, therefore, we're actually talking about using uranium-233 as fuel. To obtain reasonable amounts of either uranium-233 or plutonium-239 for use as fuel, it's necessary to place their fertile isotope in a reactor with a fissile driver that can at least initially produce a neutron field for them. The energy potential of uranium versus thorium. The energy potential of uranium and thorium as fuel in a reactor can be measured by the respective natural abundance, the percentage of fuel that fissions in the reactor, and the energy released per fission event. About 6 million tons of uranium are recoverable from the Earth. Of that amount, uranium-235 makes up 99.27%. Uranium-235 makes up the 0.72% we discussed, and uranium-234 makes up 0.0055%. This equates to about 42,000 tons of uranium-235 left to use. In contrast, about 6,500,000 tons of thorium exist on the Earth, and essentially all of it is thorium-232. The significant abundance of thorium-232 over uranium-235 is one of the many reasons thorium is being explored as a nuclear energy option despite uranium's well-established infrastructure. When fuel is placed in the reactor, it can either fission and release energy, which is good, absorb a neutron, and grow into a non-fissile isotope, or do nothing and eventually leave the reactor as waste. The goal is to maximize the amount of fissions that occur while minimizing neutron captures and the disposal of usable fuel as waste. Uranium-235 has a 5.9 thermal neutron fission to capture cross-section ratio. It's a mouthful. It basically means that it fissions 5.9 times for every one time it captures a thermal neutron and increases in size. Also, the solid uranium-235 fuel pellets, generally used in a light water reactor, also have high concentrations of uranium-238, which dilutes the neutron field. And it also builds up enough fission product poisons over its life in the reactor that after a certain point, even though there is fuel left to use, the fission process cannot be sustained any longer. When the fuel is removed, it actually still contains about 25% of its uranium-235, which then becomes spent fuel. Unlike uranium-235, before thorium can be used as fuel, it must be converted to the fissionable isotope through a neutron capture, a 22-minute half-life beta decay into protactinium-233, and then another beta decay with a 27.1 day half-life into uranium-233. Although thorium's neutron capture cross-section is not large, it actually is pretty effective at capturing neutrons simply because it has no fission cross-section and also because it doesn't have to compete with a lot of other isotopes. In the thorium reactor, though, you do have to worry about the two isotopes it creates in its transition between thorium-233 and uranium-233. Those two isotopes, which are thorium-233 and protactinium-233, both have very large neutron capture cross-sections. If either of them capture a neutron before it has the chance to beta decay into the fissile isotope, then the energy potential of that atom is lost. That being said, once thorium has successfully been converted into uranium-233, it has an 11.8 thermal neutron fission to capture cross-section ratio. Uranium-233, therefore, is significantly more likely to fission than uranium-235 when interacting with a thermal neutron. As a result, it produces less waste and has the potential of releasing more energy. The effectiveness of realizing thorium's potential energy, however, is highly dependent on how well the reactor's design protects those transition isotopes from further neutron exposure. In molten salt thorium reactors, thorium is not diluted, fission product poisons can be removed through fuel processing, and undesirable fuel compositions can be altered at power. As a result, essentially no usable thorium or uranium-233 is discarded as waste. Uranium-235 makes 2% more energy per fission than uranium-233. Although 235 actually produces more energy per fission, the ability of thorium reactors to use all available fuel, its large natural abundance, and its high fission to capture cross-section ratio makes it a better long-term fuel option for clean, reliable energy. Why other countries are choosing thorium. Obtaining usable uranium fuel for most reactor types requires massive amounts of uranium mining and enriching. The uranium-235 concentration has to be increased from its natural 0.72% to approximately 4%. To obtain about 1 ton of fissile fuel, it takes about 250 tons of mined uranium. For countries with low uranium resources or no enrichment capabilities, this can be a very cost-prohibitive endeavor. Thorium can essentially be used as is. 1 ton of thorium mining equates to 1 ton of usable fuel in the reactor. Right now, although the United States isn't really keen on using thorium, other countries like Norway and India are very interested. Norway plans on replacing solid uranium fuel with thorium pellets in their light water reactors, with the expectation that uranium prices will increase before the life of their existing reactors expire. India wants to circumvent the need to enrich uranium and draw from the rich thorium resources by using thorium-fueled heavy water reactors. Both countries are now actively researching and testing the technology. Reactor types. There are 5 basic types of nuclear reactor designs, and they're generally categorized by either their coolant or their moderator type. There's light water, heavy water, high temperature gas cooled, fast neutron, and molten salt reactors. The light water reactors can be further subcategorized into pressurized and boiling water reactors. Most reactor types can actually be designed to accept either uranium or thorium as fuel. Pressurized water reactors use a 3-loop system. In the primary coolant loop, H2O, regular water, flows through the reactor and cools the solid fuel and moderates neutrons. And the moderation process is necessary to thermalize neutrons so they can more effectively induce fission in the fuel. The water is pressurized to maintain a liquid state. The secondary loop, also water, cools the primary loop and is converted to steam. The steam is directed to a turbine, which it spins to produce electricity. The third loop, which is called the ultimate heat sink, provides a low pressure space for the steam to accumulate and a method of converting that steam back into liquid so it can continue with its secondary loop cycle. Boiling water reactors are similar to pressurized water reactors, except they only have two loops. They actually use the primary coolant as steam to spin the turbine. Uranium-fueled PW and BWRs are the two main types of commercial reactors used in the United States. Performing relatively minor design changes to existing plants would be a way to obtain the benefits of using thorium-232 as fuel without the expense of building brand new plants. Heavy water reactor designs generally resemble pressurized and boiling water reactors. One of the major differences is that while most PW and BWRs use the entire reactor as the pressure boundary, heavy water reactors use a series of individual horizontal pressure tubes that each contain its own fuel bundle and primary coolant. The moderator surrounds the tubes in the calandria, and that calandria is actually maintained at atmospheric pressure. Individual tubes can be isolated to facilitate at-power refueling. Another major difference in heavy water reactors is that they use DTO rather than H2O to moderate neutrons. D, or deuterium, is an isotope of hydrogen that contains a neutron as well as a standard proton in its nucleus. Depending on the design, heavy water can also be used as coolant. Although more common, it's less desirable for economic reasons. Heavy water has the advantage of being a better neutron moderator than light water due to its low absorption cross-section for neutrons. In fact, heavy water is so effective that your reactors don't need enriched uranium fuel. They can use naturally occurring uranium as in the fuel. India, which does not have uranium enrichment sites and has a high abundance of thorium, is vested in developing both uranium and thorium heavy water reactors. Uranium heavy water reactors use natural uranium to produce small amounts of plutonium. The recycled plutonium will then be used in fast breeder reactors, which we will discuss a little bit later, to create even more plutonium. The plutonium from the breeder reactors will finally be used in thorium heavy water reactors as the driver. The high neutron economy achieved from a heavy water moderator will increase the reactor's rate of uranium-233 production and allow it to be self-sustaining. Although not as common as the previous three reactors, high-temperature gas-cooled reactors, which have gas outlet temps of greater or equal to 1,000 degrees Celsius, have been attempted by several countries, including the United States. The high temperatures are made possible by changes in fuel design. Rather than having ceramic pellets of oxidized fuel encased in zircaloy cladding, they generally adopt a pebble bed or prismatic fuel design, where fuel little particles are coated with carbon and then silicon carbide and then placed within a graphite matrix. The unique designs were developed to withstand higher temperatures and higher temperature changes without damaging fuel. Helium is used as the cooling medium and graphite as the moderator. Higher temperature allows increased efficiency, which is one of its major benefits. These reactor designs are also very versatile and can use either fuel type, uranium or thorium, without any changes to core design. Fast neutron reactors are generally considered either plutonium breeders or burner reactors. The fast neutrons are created through the fission process, and while most reactors have moderators to thermalize the neutrons, this reactor does not. Instead, it uses liquid metal, generally sodium, as coolant. The sodium's large nucleus doesn't slow down neutrons very effectively. This type of reactor is good at plutonium breeding because uranium-235 and plutonium-239's fission cross-section both drop dramatically in the neutron field, while uranium-238's neutron capture cross-section only drops slightly. The net effect is an increase in likelihood that uranium-238 will capture a neutron before that neutron interacts with the fuel. When uranium-238 captures a neutron and emits 2 beta particles, it becomes the plutonium-239. Fast neutron fissions produce more neutrons per event, allowing neutrons to continue the fission chain reaction while still producing plutonium. The layout of uranium-238 and fissionable isotopes in the reactor affects the rate of plutonium-239 production versus its fissions. If production of plutonium is faster than plutonium fissions, the reactor is a breeder. If it's slower, it's a burner. Thorium doesn't work well as in fast neutron reactors. In fact, in the fast spectra, thorium-232 does not fission as well as uranium-238, and uranium-233 does not increase its neutron per fission count as much as plutonium-239, and both of these are very necessary parts for maintaining an adequate fast neutron count. This makes it difficult for thorium reactors to simultaneously breed uranium and be self-sustaining. Molten salt reactors have the unique distinction of using liquid fuel. The reactor uses a fluorinated thorium and lithium fluoride beryllium fluoride salt mixture that works as both fuel and coolant. An outside graphite shell moderates the neutrons. Oak Ridge Natural Laboratories created and ran an MSR test reactor for several years in the 1960s, but outside this experiment, little to no practical experience has been gained about these reactors. To maintain liquid form, salt has to be kept at very high temperatures. Although generally operated between the 450 to 800 Celsius range, MSRs can actually operate in the very high temperature range and gain the efficiency by using helium gas secondary loop, much like the gas-cooled reactors. Due to the properties of lithium fluoride salt, pressurization is not required to prevent the coolant from vaporizing, and this has the added safety of not requiring a high-pressure primary system. The United States thorium licensing process. The licensing process in the United States assumes a uranium-fueled light water reactor design, even for the new advanced technology designs. Currently, the Nuclear Regulatory Commission and the Department of Energy are working on a methodology for analyzing designs and providing licenses for the next generation of nuclear reactor technology. But even after a licensing process is in place, since thorium reactors do not have the decades of operating data to draw from that uranium reactors do, prototype testing will inevitably be required. Fortunately, the testing currently being performed in other parts of the world should help us if and when we decide to transition to thorium. But long story short, no policy is in place for analyzing and licensing thorium reactors in the United States at this time.